we will continue talking about merge sort. So today in this session we will talk of the running time of merge sort. How do we compute the running time of merge sort? So just recall the merge operation. Okay, in the merge operation we were having this array A, which this array A, okay, in which the starting index was P, the ending index was R, somewhere in the middle you had an index Q, and we said that okay, let's say we have this much portion sorted, we had this much portion sorted, and we wanted them together to be sorted again. So what we did, we copied this into a sub array called L, and we added one extra number here which is infinity. Okay, also we copied this portion into another array or sub array called R, where the last element was infinity. So each of them are sorted. Okay, each of these L and R are sorted. Okay, so then finally what we did, we merged them together into this array A. Okay, now the question is, how much time does this operation takes? So first, if you notice that, let's say between P to R we have n elements. Okay, so n elements is nothing but n1 plus n2. Okay, that means there are n1 elements here and there are n2 elements here. Together there are n elements. So if I notice in this for loop, I am going from 1 to n1 and I am simply doing a copying operation, okay, from A to L. Now this is a constant time operation. Okay, so theta of 1, and since I am doing it for 1 to n1 times, so I will do n1 operations. This one will be having again n2 operations, because each of these operations are constant time. Okay, these are called constant time operations. Okay, so essentially how much time I have spent here, n1 plus n2 is equal to order of n. Okay, or rather theta of n1 plus n2 is equal to theta of n time we have spent here. Okay, so next we go to this loop. Here we run from P to R. So we run from P to R. That means we run for n elements. So this is n times it will run. Okay, and what we do, each time we compare Li and Rj and we copy whichever is the smallest to kth position, and then we increment our k as well as I or j, whichever is appropriate, right? So how many times this loop will run? N times. How many, all of these operations are constant time operations. So what is the total time taken by this loop? Again, theta of n. So essentially this merge operation total in all together takes theta n of time, where n is equal to r minus p plus 1 or n1 plus n2. Okay, whichever way you want to say. So that is the time taken by the merge operation, but that's not enough, right? We have to compute the running time of merge sort. So essentially now we have to figure out how much time it takes to solve the sub problems. Okay, so we do that using the recurrence relation. Okay, so whenever an algorithm contains a recursive call to itself, its running time is described by a recurrence equation, or simply called recurrence. Okay, so let's say Tn is the running time of merge sort for an array of input size n, or let's say there are n elements to be sorted, and Tn is the running time. So there are 3 steps, if you recall, in a divide and conquer strategy. Even merge sort has 3 steps. First is divide. So how much time is taken to compute divide? Division in merge sort is nothing but computing the middle index. Q, recall, you compute Q, which is nothing but R plus P divided by 2. How much time that takes? It's a constant time operation. Okay, there is a addition, there is a division. Those are constant type operations. So it takes constant time. So the divide step computes the middle index in constant time. Okay. The next operation is your conquer. So essentially now you divide into two sub problems and you try to solve two sub problems, right? So you have the conquer strategy which you want to work on sub problems of size n by 2. Okay, how many sub problems you have? Two sub problems, right? Each of size n by 2. Then you want to combine the solution of each of the sub problems. So let's say in the merge sort you got two sub arrays and those sub arrays have been sorted. In the combine step, that is the merge step of the merge sort, you want to merge these two sub arrays to get your final array, sorted array. Okay, so the combine step we have just seen that takes theta n time, where n is nothing but number of elements in the array. Okay, fine. So we can then write our recurrence relation of the running time as follows. We can say Tn, this is the overall running time of merge sort, is equal to twice Tn by 2. That means time taken to solve two sub problems of size n by 2 plus theta n, that is some extra time is required for the combining operation. Okay, how much time? Theta of n. Okay, and when is it true? When n is greater than 1. Why? What happens when n is equal to 1? What goes wrong? Well, when n is equal to 1, that means there is only one element. If you recall in merge sort, we don't even do anything. Okay, that means it's already sorted. Fine. So there is nothing further to divide, there is nothing further to conquer or combine. Okay, so one element is there, it's sorted in itself, we are done. So how much time that takes? Again, constant amount of time. So Tn is equal to theta of 1 if n is equal to 1. Okay, so if there is only one element, Tn will take theta 1 of time. So this is important. Both of these conditions are important. Okay, so now if you notice what is happening in a recurrence relation, you are writing Tn, the problem of size n, as some combination of sub problems of smaller size n by 2. Okay, fine. So now let's see how do we represent it very cleanly. Okay, so we say that okay, Tn is equal to theta of 1 if n is equal to 1 and is equal to 2 times Tn by 2 plus C of n. Okay, so rather than saying theta of n, we are using a constant C times n. Theta of n means it is bounded above and below by some constant time n, right? Okay, so we are using a constant time n, okay, if n is greater than 1. So now how do we solve this recurrence relation? Now one thing is very important here, there is something called the base case. If you have to solve this, any recurrence relation, see, you got a big problem, you keep on reducing the size of the problem, but you at the end you have to reach to a position where the problem is so simple that it's very trivial to solve. Okay, but that's the base case which you need to mention in your recurrence relation. Okay, so that's what we are saying, Tn is equal to theta of 1 if n is equal to 1. Now let's try to solve this recurrence relation. Okay, so here is the solution to the recurrence relation. So what we do, we say, oh, Tn is equal to twice times Tn by 2 plus Cn. We have seen up till this much. So this is nothing but twice times, I am keeping these third brackets on and I am unfurling this Tn by 2. So just put n by 2 in this position. Okay, so if I put n by 2 here, what happens? This is 2 times T n by 2 whole square plus C n by 2, right? So this is what we have written, twice Tn by 2. This is nothing but twice Tn by 2 square plus Cn by 2 plus Cn. So if I just solve this, this is nothing but 2 square Tn by 2 square plus Cn by 2 times 2, which is nothing but Cn. So this Cn plus this Cn makes it twice Cn. Okay. I again unfurl it little bit further. So I will say that, okay, let's unfurl this Tn by 2 square by simply substituting this guy here. Okay. So it is nothing but 2 square, again third brackets, and I'm going to say, though this is nothing but twice Tn by 2 square by 2, that is n by 2 cube, plus Cn by 2 square. Okay. Plus 2Cn. So again, if I solve this, this is nothing but 2 cube Tn by 2 cube plus 2i square, 2 square and 2 square gets cancelled. You got another extra Cn, so this becomes 3Cn. So if you keep on doing this one after another, you will get at some point 2 to the power k T of n by 2 to the power k plus kCn. Okay. Right? Just look at this and look at this. They are similar. Okay. Fine. So that's what we will get. So now let's say that if your n by 2 k, this is essentially nothing but the problem size, has been reduced to unit size 1. Okay. This n by 2 to the power k is now 1. If that happens, what happens? I have reached to the base case. Okay. That means I can say that, okay, n is equal to 2 to the power k, which means k is nothing but log n to the base 2. Okay. Just take logarithm on both the sides. You will get k is equal to log n to the base 2. Also, we have already seen that T1, that is Tn is equal to 1, is theta 1. Right. So together, if I just substitute these two things here, what do I get? 2 to the power k. What is 2 to the power k? 2 to the power k is nothing but n. Okay. 2 to the power k is nothing but n. So we will say that, okay, n times, so you get this one as n times t n by 2 to the power k. N by 2 to the power k is nothing but t of 1 plus k is nothing but log n to the base 2 times Cn. Okay. What is T1? T1 is theta of 1, you know that. So this is nothing but n of theta of 1 plus Cn log n to the base 2. So this is nothing but, together I can say, okay, this is nothing but theta of n log n to the base 2. Okay. So we have solved our recurrence relation. So T of n is equal to theta of n log n. And that's the running time of merge sort algorithm. Okay. And this method of solving the recurrence equation is called iteration method, where we keep on substituting, you know, the original expression for the sub problems. Essentially, we will unfurl it, get a long summation. We will simply solve that summation. Finally, what we will get is the solution to our recurrence equation. So we got the running time of merge sort as theta of n log n. Thank you.